I am an assistant professor at University of Washington, D.C. I just joined last September. And I'm leading the Wearable Intelligence Lab at UW, which we focus on a lot of physical human environment interactions. They embed and convey tons of information. As an example, at this moment, all of you are sitting on a chair. And the sensory system throughout your body is constantly capturing the physical interactions between your body and surrounding. And this would include pressure distributions, vibrations, temperature, and so on. And such data will be fed to your brain, which process such information and generate signal to drive the muscle, and therefore allow you to balance your body and balance your posture and so on. And our research goal is to build a wearable intelligent assistant which will be able to replicate such sensing, modeling, and augmentation capability through sensors, AI agents, and actuators. But we need to deal with a few unique characteristics of physical interactions, which are pervasive and diverse. So such physical interactions happen throughout our human body at extended durations, under diverse using scenario, and also subjectively perceived by different individuals. So even if we are grasping the same cup of coffee, I might feel it's too hot and you might feel it's too cold. So we are trying to address these challenges by answering the research questions on how to efficiently scale up the sensing and actuation interface so that it can cover a large coverage area, serving different parts of our body, and how to seamlessly integrate such functionality so that it can serve us at extended durations, as well as how to make the sensing and actuation interfaces robust and adaptive to different individuals and different using scenarios. And we are trying to address this by using the power of digital fabrication of wearables. And more specifically, wearables in this presentation is textile. So we use textile because textiles are around us. So the tablecloth, the garments, and the curtain and carpet, they are all made of textiles. It's one of the very few platforms that has direct contact between our human body at extended durations. We wear garments every day, and even though when we are sleeping, you interact with your pajama and with the bed sheet. It also has a very long history in industrial manufacturing, making it compatible to the digital fabrication capability, making it low cost and compatible with mass manufacturing. And by leveraging such intelligent textile that can cover a large surface area, capturing information continuously 24 hours a day, we hope we'll be able to capture a diverse and scalable data set, which is very valuable for the skyrocketing AI technology, allow us to address the diverse nature of physical interactions. So this is one example of our work back in 2021, where we presented full body tactile sensing garments, which can capture the physical human environment interactions. So each individual pixel is a pressure sensor, capturing the continuous pressure distributions in real time. And by having a whole array of such tactile sensors, we'll be able to capture both contextual and spatial information. And by leveraging those information, we can classify the real-time sitting postures of a user, as well as to predict full-body human posture by only using the tactile sequences without any visual feedback. And more importantly, such garment is enabled by a digital machine knitting process, which is the industrial textile manufacturing techniques, enabling a low-cost and customized fabrication approach, enabling a sensing interface that can be full-size and spanning a large area. And later, we extend a wearable interface to an ambient sensing interface that can seamlessly integrate in the environment. So here is an intelligent tactile sensing carpet, capturing the real-time pressure distributions with different people doing different kind of exercises on it. And by leveraging the power of machine learning, we can also predict full body pose in both a single person and multi-people scenario, only looking at the tactile sequences captured by the carpet. And such system address the constraint of visual occlusion or limited field of view of vision system, and has been applied for applications in AR, VR, and study on human biomechanics, thanks to its capture quantitative information. And more recently, we'll also demonstrate a 3D human pose estimation by integrating IMU on a loose fitting garment. So conventional approach usually requires a tight fitting garment to avoid the inaccuracy of sensing information and the drift of the sensors. So we actually leverage the power of machine learning to compensate the inaccuracy and drift of sensors by coming from the loose fitting garments. And we are also very interested in multimodal sensing. So here we demonstrate a synchronized multimodal data acquisition setup, capturing on how humans would perform kitchen-related tasks. So beyond the physical information, such as tactile sensing, hand pose, and muscle activity, we also capture synchronized visual, audio, and label, text-based label, which is a more established modality. So we are hoping that we'll be able to use such more established modality to use it as a reference or supervision to help us understand such elusive physical interactions, to help us extract insights for further exploration. And beyond sensing, we also work on some actuation. So here is the digital machine-knitted pneumatic actuators, serving as assistive wearables to help people's bending of their elbows. It comes together with interactive user interface, allowing users to place the actuation areas, sensors, and visualize the deformation of it. It generates the design files automatically and sent to the digital fabrication process for immediate fabrication, allowing a low-cost and customized fabrication pipeline. We also combine sensing and actuation to realize the transfer of interaction. So here is an example of how we do the tactile interactions transfer. So here is a piano learning scenario, and the teacher is wearing a tactile sensing glove, capturing their finger pressing sequence. And we are translating such information to the student who is wearing a vibrotactile haptics glove, perceiving the real-time finger pressing sequence from the teacher, and therefore encouraging them to learn a more optimal finger pressing sequence. And what's interesting here, it's not in the slide, the generation of the vibrotactile haptics feedback is actually from some AI model, which takes into account of the personalized behavior. One very interesting characteristic is that whenever we perceive some kind of haptic feedback, we will spend some time to thinking about what does this haptic feedback mean. And this time of reaction is different from person to person. So that is one example of what we are dealing with the AI model in between, generating an adaptive haptic feedback to the specific users. We also apply such system to a teleoperation setup. So here, a user on the top right is teleoperating a parallel gripper with their thumb and index. So the parallel gripper is equipped with tactile sensors, which capturing the real-time forces and transfer it to the users. And the users will be able to control the gripper in a more optimal way, especially when interacting with such deformable objects. Again, this is enabled by a digital fabrication pipeline. We use digital embroidery to integrate both the sensors and vibrotactile haptics. And interestingly, both the knitting machine and embroidery machines from Japan, so I guess this is the best place to present the work. And so a lot of our applications will be focused on both humans and robots. So rehab would be a very specific example on how to use such sensing and actuation interface to encourage users when they are doing in-home rehabilitation to guide them through the correct sequence to avoid a second injury. It can also apply on robots. So as Andrea mentioned, humans' hands are super flexible, super dexterous, with a huge capability to perceive the physical objects, but robot doesn't. So we are trying to equip robot with human-like sensing capability to help them perform more delicate operations, such as grasping on such deformable objects in a safer way. We can also extend it to a larger scale, like equipping a full-body tactile sensing for robot, so allow the robots to have some kind of sensing capability around their body, which will open up new opportunity. For example, like the robot dog using their body to hold the door, using their back to carry objects, carry rotating objects and things like that. And we are also hoping to democratize our technology by developing some kind of toolkit, which will be presented at CHI, late-breaking work. So we present some kind of user interface where users can import arbitrary 2D and 3D objects and then can identify where they want to place the sensors and generate a file for immediate fabrication. It has some kind of optimization pipeline behind it, allowing users to identify some higher level abstraction on their objective and therefore optimize the sensor placement and also firmware setup and so on. And in summary, we are very interested in digitize physical interactions, just like how people do it with images, audio, and text, and so on. And when we think about the path of AI with images, text, and so on, it benefits from the huge amount of data set, which is coming from the low cost and off-the-shelf input and output interface, like the cameras, microphones, speakers, display, and keyboard, and so on. So I'm hoping we will be able to get into a low cost and scalable and democratized input-output interface for physical interactions as well. And I think that would dramatically promote the path of AI in such physical interactions. Also, in terms of getting back to the wearable intelligent assistant, I hope it can not only sense and also provide feedback back to the user to promote their action. A very important component in between is some kind of AI agents that can interpret such high-dimensional sensing information and also generate an adaptive and effective feedback back to the user depending on the scenarios and the user themselves. So I think this AI agents would be a huge benefit to such intelligent wearable assistant. And with that, thanks for listening. I'm open to any
questions. I have a question. I'm wondering, this tactile stuff, like, is it like simulating human skin intelligence? And I feel like the skin is the biggest, the largest organ, right? Mm-hmm. So what kind of intelligence you draw from the human skin? But I see, like, creating these moves is more like beyond our current skin ability. So what kind of intelligence you cannot simulate in the tactile?
Yeah, so tactile is only one example of physical interaction. You are right that there are many other modalities as well, like the movement of your joint, this kind of proprioception, and also muscle activity and so on. So in my opinion, all of those modalities should be comprehensively captured. So that would be one of the example of where we are doing this multi-modal data capturing setup, not only tactile, but with also proprioception, which is the hand pose, full body pose, muscle activity, and so on. We are replicating such tactile sensation for multiple reasons, because we think it's the easiest way to apply the power of AI at this point, because when we look at the tactile sequences, it's actually very similar to images. It's pixelized. So we can apply a lot of the established algorithm to help us to starting to extract insights from there. So that is one reason why we start from here as well.
Great. If no other people have questions, yeah, go ahead. Yeah.
Hi, I'm Xuan from Huawei. We have a more convincing scenario for business. Now we are researching on a similar intelligent textile direction. In China, SUVs above $100,000, Huawei has occupied is the #1 shipment of this level of cars, and we are researching on seat with smart textile to help the passenger to get a better experience, just like I think better than business class seat. But there are many problems. First one is it can only detect your length, but not your weight. And the second is when you wear thick clothes and in or you adjust the postures when you sit on the seat, the data is not stable. But we still have some advantage since we have one account for cars, smartphones, and watches. You know, Huawei smartwatch, the shipment of Huawei smartwatch is #1, surpassed Apple last year. So we want to integrate all this information to help the smart textile to implement it first on the smart cockpit. So I'm not sure if you do you have any ideas to how to solve the weight problem and the different posture problem on the next level seat.
Well, yeah, first of all, I am very glad to see there's a huge business market out there for this kind of thing. That's nice. And I need to admit that there are a lot of problems on textile. But I think for the weight, you can actually capture weight from here because you can calculate the continuous pressure distributions at each point and then sum it up, and that will be the weight of the person. But in my opinion, a bigger problem would be because whenever you want to integrate functionality on textile, you want to maintain its flexibility, its capability to conform or fit into different human body. But all the cables coming out from the sensors might be a problem, right? And you need to have some kind of controller coupled with the sensors and actuators and the power sources, and how to make it detachable, and then how to make the smart textiles washable. I think and how to make it robust, because the textile are moving around all the time. It's not like a hard interface that can maintain stability for a long time. So I think a lot of those are open questions for people from different areas to work on it together.
Super interesting work. What I think inspires in terms of questions and comments is there's the narrative that says, large language models have been fed already all possible human knowledge that is in text. There's no more that they can be encoded, on it. So the next frontier is like we're more than just text, vision, audio. And I'm thinking about new kind of data sets that is about, the human body and its motion and its posture. And in the same way that current large language models have a certain opinion about theory of mind. They can give opinions about people's theory of mind. I wonder if there's something akin to theory of body. Given body data, I wonder if there will be a new generation of models that, based on your technology, are able to actually give you a theory of body that can be applied on all sorts of kind of scenarios that include business, health, productivity, etc.
Yeah, I'm pretty sure there will be, because I think physical interactions have very different capability. For example, data set is very expensive, right? So you for sure will have smaller amount of data. Then how to make a generic model that can be trained using smaller amount of data, and how could you, it's also more adaptive to different individuals, in my opinion. Just like Junie mentioned, everyone's unique, right? So I think the generative model should also take that into account. And I also feel like to start with, it might be interesting to start with a specific group of people who would be willing to sacrifice for having an uncomfortable textile for now, but can collect some data, train some model to show some preliminary data on improvement. For example, patients, like you mentioned. I think that might be an interesting first step.
Okay, thank you very much. I think we just conclude a second session, and on the schedule we